You are live.
Good afternoon and welcome to the panel on utilizing ISRU. The main message that I personally want to make today is that ultimately human exploration of space is non-sustainable unless we learn to live off the land and other planetary surfaces. For example, the massive fuel, assuming LOX methane, to get off a Mars ascent vehicle off the surface with 3 astronauts aboard, about 33 tons. How much more sustainable would our Mars presence be if we could produce that fuel from Mars resources? So the first question is, what are in-situ resources? In essence, they are the stuff that is available to us in the planetary environment that can be used to enable and sustain robotic and human activities. Future astronauts and maybe semi-autonomous robots will need to collect space-based resources and transform them into breathable air, water for drinking, hygiene and plant growth, rocket propellants, building materials, and more. Mission capabilities will increase and presence will be more sustainable when useful products can be created from in-situ resources. I contend that if we don't learn to live off the land, we won't get far and we won't stay long. It will be Apollo all over again. Which raises a question about future exploration architectures. Do we design these to be quick and cheapest way to get there? Or do we design them so that we can evolve them easily to make use of space resources and be truly sustainable? An example is the use of cryofuels for descent and ascent vehicles, such as LOX hydrogen or LOX methane, which can be derived from space resources as opposed to storables. Currently, we're developing the capability to return humans to the lunar surface using the Artemis program. Very exciting time. There's much we can do during these activities to reduce technical risk, cost, and schedule for future human missions to Mars. In preparing for such missions, there are 2 types of capabilities that we need to develop, as noted yesterday by Jim Morhard. Those that are unique to Mars, like extraction of oxygen from the atmosphere, which we'll hear more about today, and those that we can develop, test, and prove on the Moon prior to going all the way to Mars to find out whether they work or not on another planetary surface. Aspects of the capture and processing of water from ice deposits fall into this realm. It's important that as we develop the lunar architecture with both robotic and human missions, we take a path that is, to the extent possible, leverages those activities in preparing for humans to Mars. This is especially true for resource exploitation, where we have a long way to go before we get to commercial production levels. Given the critical role of resources in the future of space exploration, we need to identify and characterize important resources on the Moon and on Mars. We also need to move rapidly forward with in-situ test beds to develop extraction and processing capabilities that can be scaled to production scale facilities, preferably owned and operated by commercial entities, in order to sustain human presence beyond LEO. So we've got a long way to go, but there is a lot to do with space resources. With that brief introduction, I want to introduce my colleagues who bring a diverse range of perspectives and capabilities with respect to resource characterization, capture, processing, and management. Each is going to give an introduction, a presentation on their work and provide their perspectives on space resources. We'll hold questions until after all the panelists have spoken. The first speaker is Kris Zacny. He is the Vice President of Exploration Systems at Honeybee Robotics. His expertise includes space mining, in-situ resource utilization, robotic terrestrial and extraterrestrial drilling, and geotechnical systems. He's field-tested space mining hardware in the Antarctic, the Arctic, Atacama, and Greenland. He's currently developing space mining hardware for various missions such as Viper and Dragonfly. If you want to know anything about drills anywhere in the solar system, he's your guy. Leslie Gertsch has a PhD in mining engineering and is an associate professor of geological engineering at Missouri University of Science and Technology. She runs the Space Resources Laboratory there and the Space Resources Graduate Certificate Program. She's been adapting terrestrial mining methods for use on the Moon, Mars, asteroids, and comets since the 1980s. She brings a touch of reality to the discussions of establishing large-scale mining operations on other planets. Dana Hurley is a planetary scientist at Johns Hopkins Applied Physics Lab. She uses spacecraft data and modeling to understand the dynamics of volatiles on planetary bodies with an emphasis on application to water on the moon. She is project scientist on the Lunar Surface Innovation Initiative, in which APL is supporting NASA Space Tech's initiative to develop the technology that will enable a sustained presence on the moon. You're going to hear more about that. Michael Hecht is the Associate Director of the MIT Haystack Observatory and Principal Investigator for the MOXIE experiment on the Perseverance rover. MOXIE will demonstrate a core ISRU capability, making oxygen from carbon dioxide in the Martian atmosphere. Michael's broader Mars scientific interest includes studies of contemporary polar processes, atmospheres, and soil. Prior to coming to MIT in 2012, Michael spent 30 years at NASA JPL, where he led the MECA instrument on the 2008 Phoenix lander that first identified perchlorate as a significant component of the Martian soil and returned findings pertinent to astronaut safety on Mars. As a demonstration of the breadth of his expertise, he's the Deputy Project Director of the Event Horizon Telescope, the collaboration that released the first image of a supermassive black hole in 2019. Quite a breadth. Anyway, with that, I will pass the baton to Kris Zacny for his presentation.
Thank you, Steve. Wait, could you bring up slides, please? As the slides are coming, I just want to say that I'm coming sort of from a pragmatic standpoint in terms of ISRU and Mars mining. In my previous life, I worked in a deep South African mines, all the way down to 12,000 feet deep. I've seen anything you could imagine in terms of equipment breaking, and in terms of machine versus rock always wins. So with that, I prepared a couple of slides to give you sort of a taste of how we should approach ISRU to make sure that we are successful. And it's important we do it right, because if we got it wrong, we won't be able to come back from Mars. So first slide, please. And I'm not sure whether I can. Okay, great. So two critical points. It's really important to look at terrestrial technologies first. Terrestrial mining has been done for thousands of years. We came up with many different ideas, and some of them obviously failed, and those that worked, they sort of moved on up the technology chain, and these technologies actually you can see every day in a mining environment. Second, it's also important to evaluate those technologies in Mars analog sites here on Earth before we send something to Mars. So these two statements essentially boil down to, first thing, if we fail digging here on Earth, we are bound to fail on Mars. And proven technologies have a higher chances of succeeding on Mars. So let's look at what we've done here on Earth first. Next slide, please. This is Mars. This is Mars Phoenix, the spacecraft that landed in the northern polar regions of Mars. As far as you can see, it's rocks. As Mike mentioned earlier on, actually Steve, when introducing Mike, Mike's instrument discovered perchlorates in the soil that have tremendous implication to ISRU. But if you dig a couple of inches below the first, these rocks and the regolith, what you're gonna find is ice, like the pictured on the right-hand side. These bald patches is pretty much pure ice underneath a couple of inches of regolith or ice cemented ground. And this stuff is as hard as a rock. So again, we have some regolith, a bunch of rocks, a bit of regolith, and ice underneath or ice cemented ground. Next slide, please. This is not Mars. This is Antarctic Dry Valleys. It's approximately 45-minute helicopter flight from McMurdo Station. It's a really beautiful and picturesque site on Earth. I spent a couple of weeks digging holes and drilling holes and learning how to actually do this. If you look at this side, what you see is rocks, a lot of them, just like on Mars. If you were to dig deeper, what you'll find is this couple of inches of what we call the desert pavements of very, very dry soil overlaying ice and ice cemented ground, which again is as hard as concrete. And our latest results show that the soil, just like on Mars, has actually perchlorates as well. Maybe it's slightly different concentration, but it does have these perchlorates. So you don't have to go very far to be on pseudo-Mars. These sort of locations, Dry Valley is just one of the good locations to test your hardware, but you can go to Atacama and find, also very, very nice and relevant locations. So with that in mind, let's shoot to the next slide. I want to show you just one of the technologies that we're working on, and there are numerous other technologies like gypsum extraction that Paul van Sousand is developing. We're doing gypsum here on Earth. There is gypsum on Mars as well. In this particular case, I want to tell you something about the project we called Redwater. It combines two proven terrestrial technologies. The first one is called tubing. On the picture on the left-hand side, it's essentially a metal tube that's wound on a drum and goes through an injector. And as it goes through an injector, this round steel tube becomes straight tube. At the bottom of the straight tube, you have essentially a drill bit. So that's how you're drilling. You have, your drill pipe is essentially a so-called cold tubing. There is another technology called Rodriguez well or Rodwell, and this technology is used every single day in the South Pole of Antarctica to mine water, liquid water, from tens of meters below the surface into the tank to sustain human presence in the South Pole. The way it works is you drill a hole, you melt ice, and then you pump water to the surface. So Redwater combines these proven terrestrial technologies into a single system pictured on the right-hand side. And what we're after is these glaciers or ice sheets buried, below, meters or tens of meters of regolith. We can poke a hole using cold tubing, and once we're in a hole, we can establish Rodwell to melt ice and pump water straight into the tank. We're doing a lot of testing in our cold room, and pictured on the bottom right-hand side is some of these tests. This ice block is essentially 1 meter by meter by close to 1 meter. And one of the tests that took 15 hours, we melted almost 100 kilograms of ice. We turned it into water. This red, we dyed the water in red, so actually you can see it right through the eyes. We used 1.6 kilowatt of electrical power to melt, and we rotated the bit to stir up water and enhance melting. But if these production rates are sustainable, you can mine 3 tons of water in approximately a month. So again, this is nothing. I'm not reinventing a wheel. I'm using technologies that have been proven in a terrestrial environments and making it fast forward to Mars applications. Thank you.
Hi there, I'm Leslie Gertsch. I'm going to be talking following on with what Kris has said. Could I have the first slide, please?
These are Dana slides.
Well, while they're coming up, I've only got 2, so I can go ahead and start talking on them. And there aren't any pictures. There we go. Point I want to make is that nature makes minerals, but it's people that make mines. And Kris has told us a lot about what we know in technology, and I want to make a little bit wider view in technology fits into this. The first point I want to make is that mineral deposits are natural things. They are places and times, really, but places where minerals have been concentrated by one or usually several natural processes, sometimes acting on human timescales, but sometimes acting on geologic timescales. An ore body is a mineral deposit that can be processed to give a net benefit. This is where people come into it. And of course, the equation that's next there is the same old equation of business. The net benefit is the difference between the gross benefit, for example, calculate or surviving with life support or making fuels and propellants, minus, of course, the costs that are involved in making them. Nothing's free. Let me get back to my notes here. Yes, the gross benefit comes from the ore body, from the material, but the costs come from the engineering. And of course, the main difference between science and engineering is science figures out how things are, and engineering takes that and makes things happen that we want to happen. Of course, every scientist is part engineer, and every engineer is part scientist, so it's not easily separable. Next slide, please. Okay, what humans actually need from Mars, or the information we need in order to produce materials that turn our presence on Mars from a giant camping trip into an actual sustainable series of civilized activities, are several questions we need to answer. One is what's the production rate we're going to need? And that goes back to what humans actually need. We've been talking about water and actually other volatiles, and we'll hear more about that from Michael here in a bit. We need them for many things, but potentially we'll get them from the atmosphere. That's what Michael will talk about. We'll get them from ice, which, by the way, is a mineral. We'll get them from other minerals that have water or hydroxyl in their formulas, in their mineral formulas. And we can also get ores from the waste materials from human activities of all different kinds. We'll be needing, from the minerals on Mars, water, of course, as I mentioned, but also structural components, things like metals, which you can get from unconsolidated materials, or you can get from solid rock, either igneous, which is what we often think of on Earth, but you can get metals from some sedimentary deposits as well, and there are sedimentary deposits on Mars. We haven't found metamorphic rock as such yet, but I suspect it's there. We just have to get there and look. We can also get non-metallic mineral or materials from, and that's basically construction materials, sand and gravel, which are size terms, not so much compositional, but this is where we can get into co-production and by-production of several different materials from the same scoopful of regolith or broken rock. Now, mineral engineering deals with constantly changing spaces. There's a physical space, because once you find a deposit and you set up a mine, you're moving material. So the mine configuration continually changes. It is not static. It's definitely dynamic. And you have to be careful that dynamism doesn't interfere with some of the infrastructure that you're trying to set up. Mine engineering also has to deal with time, and that's affected also by properties of the ore body. Consistent production rates, which make it a lot easier for people to plan, are controlled by variations in the ore body properties. Obviously, grade or concentration of the target mineral is one of them, but also the concentrations of other materials that either you just don't want, or that poison or negatively affect the process that you're using for extracting the material that you do want. And of course, as we go through all of this, and as the demands for the output increase, or hopefully not decrease, the trade space changes. And that's before we even get into things like terraforming or any of that. Now, the mining method It actually depends on deposit characteristics, the geometry of the deposit, which is very likely going to consist of various different ranges of grades, as I mentioned, of the ore and the waste. The type of ore, we can get copper from sulfide minerals, we can get copper from oxide minerals, but how we process them is very different for the two. And you don't want to set up a plant for sulfide source and find that you've only got oxide source, to make things simple. Ground control. When you're digging a hole in the ground, some of the material you want to break and put where you want it to be so you can work with it. Other material you want to be sure stays in place. You don't want the sides of the pit sliding down on you, or if you're underground, you don't want the ceiling caving down on you. The geomechanical behavior of the ore and waste controls the different ways that we can obtain the material. If the ore, for example, is a stronger material than the waste, we have different methods of extracting the ore safely than if the waste is stronger than the ore, or if they're both the same strength. As I mentioned, the mine configuration is always changing, and so is the production scheduling. That has to do often with the variation of grade throughout the deposit, that to give your processing plant a consistent feed to make it most efficient, then often you have to segregate ore from different parts of the mine, store them, and then blend them to a proper mix for feedstock to the mill. And of course, the other installations that we're going to have on Mars have their own geotechnical constraints. Now, town site, you don't really want it to be on a really steep hillside, but if you put it on the flats, one of those places might conflict with where your deposits are. Power source we've just heard about in the previous breakout session, and it's got its own constraints, and also there are special science regions that we'll need to watch for and not contaminate or otherwise affect. So I'll leave it here, and we'll go on to Dana, and she'll tell us more.
Hi. Let's see here. Okay. So I want to take a brief look at an enabling step on the path to Mars, and that is the moon. I want to introduce to you all the Lunar Surface Innovation Initiative, which is LSII, and LSII is something that Lee mentioned in his remarks in the earlier session. So LSII is NASA's initiative to develop the technology for sustainable operations on the moon. And we know that the Artemis program is an ambitious program, and that living and working on the moon or any other world, living and working off world, is enabled through technology. And in order to have exploration become sustainable, we need to build up the infrastructure that supports future missions and improves the capabilities off-world. And so the LSII is working on the technologies to make the mission sustainable. And our development is in 6 different technology categories. Let's see. The first one is ISRU, and ISRU stands for in-Situ Resource Utilization. That's the topic that we're covering here in this panel. And on the moon, ISRU means looking for the propellant that we need to fuel future missions and that sort of thing. So on the moon, what we want to do is we want to mine some of the water that is stored in the permanently shadowed regions on the moon. And the ISRU that we want to do on Mars is going to be different, but showing that you can harvest resources and use them and count on them for future exploration is a really important activity that we want to prove out on the moon. The other technology areas that we're working on in LSII are extreme access. That is the ability to land at a particular point, have access to any place that you want, robotics to get you around once you're there, and communication infrastructure to enable all of that. There's also excavation and construction, and that's interacting with the regolith and using it to build structures and to get at the resources that you need. Then there's dust mitigation, which is an issue on the moon in terms of having dust that sticks to everywhere. On Mars, there are also dust mitigation issues, although they are probably going to be handled in a different way. Power is something that we need to enable every activity that we're going to be doing off-world, and so having the ways to harness the power and provide it to all of our activities is another technology that we're working on, and that was the topic of the previous session. And then extreme environments, dealing with the thermal environment, the radiation environment, the illumination environment, all of those different, the space plasma environment. Those are things that we need to learn how to handle and develop the technologies that can survive the extreme environments that exist. So the key thing here is that all of these different technologies are interrelated, and you need to have technologies available for all of these, and you need to approach that development in a systems perspective, so that when you're developing your power system, you have it so that it's going to be able to supply the power that you need to your ISRU systems, to your rovers, to your excavation machinery, to your dust mitigation systems. And so when this technology is all being developed, when you approach it from a systems perspective, then you're going to be able to more easily integrate it all and have it work together as a system once you deploy it off-world. So, NASA is going to the moon and then to Mars. And so the moon is a proving ground for deep space exploration. There's a very ambitious schedule for development, the lunar technology. And we can learn a lot of that, from that, on how to apply that to the Mars technology that we want to send humans to Mars. The consortium style approach to developing the technology that we're using for the moon is something that we can leverage for Mars technology development. And then having commercial sector involvement and international involvement is really enabling. You can also learn a lot about astronaut health and safety through the moon as a proving ground. And so once this is all developed, then that's going to supply propellant that's needed for deep space exploration and the deep space economy. And it's going to bring together a bunch of diverse stakeholders that are really invested in making sure that we can have access to whatever part of space that we want for exploration, including Mars. So thanks. And next, I think we have Michael.
Mike, it looks like your mic isn't working. You might want to unplug it and plug it back in, sir.
Testing 1, 2, 3. Is that working better?
Gotcha.
Yes? Okay. I think that was a yes. All right, everyone's nodding. All right. I'm also going to try I'm talking without slides here just to remind myself that it's possible to do that from time to time, so you get to be the guinea pigs. What I have in common with, I think, with Kris and Kris's presentation, Kris Zacny's, is that I strive to be a sort of practical innovator. In other words, I like to look over the next hill at things that could be done soon. And while I think it's fascinating to think about what we'll do in 10 years, and 15 years, and 20 years, that's not really where I put my emphasis. So I want to talk about how we phase some of these things in, okay? And I do want to focus my attention on Mars because, well, it's my second favorite planet, and that's what I'm interested in. So let's start by thinking about a thesis that our utilization should, I'd say, obviously be commensurate with the infrastructure we have in place. So there's some things we can do robotically with near-term capability. There's some things that really need a human presence or are more practical with a human presence. We can do all sorts of things robotically, but it may be more work than just waiting until we have boots on the ground. And then think about what we can do when we really have a permanent established base, okay? And as I said, my interests are in the earlier stages. So let's walk through our resources. In-situ resources are a very broad category. And I think Steve in the introduction mentioned the term, he mentioned something about transformation. And I often like to distinguish that term in-situ transformation of resources from utilization of resources. But let's start with resources in general. Sunlight is the most obvious in-situ resource. It's the easiest one to utilize, at least in the daytime. On the moon, what you do during a 2-week night is a big problem, of course, but in the daytime, it's easy to use. And we already use it for power. We've done that for a long time, starting with Pathfinder. We sometimes use it for heat. If you think about the machinations to make sure that Spirit and Opportunity are in the right slope in the cold times of the day, so they get lots of, so they stay warmer. And we even built a payload for the 2001 Surveyor lander called MIP that was a precursor to MOXIE, actually, but it used solar-derived thermal cycles to collect carbon dioxide from the atmosphere. So we use sunlight for power and we use it for heat. And it's great and it's easy and we don't need to talk about it more. Atmosphere is the next thing in that hierarchy, okay? It's more difficult to use than sunlight, but it's everywhere. You don't have to prospect. You don't have to mine. You don't have to go anywhere. You don't have to retrieve it. You don't have to find anything. You just have to be like a tree and breathe it in and breathe it out and do things for it with it. So for example, today we already use that resource. How do we use it? We use it for braking when we deploy a parachute. Okay. We've even used it as a cleaning device on, again, on Spirit and Opportunity, on MER, for cleaning off solar panels, where we just wait till the dust devil comes around and that cleans off our solar panels and we get more power. So we've used atmosphere in a passive way. Now, MOXIE, which I'll talk about in a few minutes, is going to give us the capability to transform atmosphere, and transforming the CO2, which is the dominant component of the Mars atmosphere, into things that we can use easily robotically. Again, we don't have to go anywhere. We just need a mechanical tree to do this. So the primary use is oxygen. The primary use of oxygen is for propellant. But of course, we also, as human beings, like to breathe it. And those two things have more in common than you would think. I'll touch on that in a moment. But oxygen is not the only product. Carbon monoxide, CO, is a product, which is very useful for some simple reasons, such as being able to burn it again with oxygen in a fuel cell. It's a very useful power source for electricity. And again, and not only for electricity, but it can be used for surface transportation, for example, again, in a fuel cell mode. Now, the second thing you can do with CO, if you have water, is you can do all kinds of interesting chemistry. You can make anything from methane as fuel to vodka, if you like, if you have CO and if you have water. And Kris talked about some of the technologies to get water, and I'll get back to that in a moment. But the other thing that you can do that doesn't come directly from MOXIE, but is related, is if you're separating gases, if you're separating constituents, CO and CO2 and oxygen, you can also separate out the inert gases, the nitrogen and the argon, which are about 4 or 5% of the atmosphere. And we need those inert gases. We need them in a habitat. We can't breathe pure oxygen. We can't breathe oxygen and CO2. So those gases are important. And should anyone ever want to use an internal combustion engine, which is amazingly efficient, by the way, the only reason they work on Earth is because we have all those other inert gases to heat and expand and push out a piston. And so again, inert gases are valuable. So the other thing we could do, by the way, with the atmosphere, and I have another activity we're trying to propose this with colleagues, is to use it for wind power. Okay, we haven't done that yet, but it's not difficult. As Kris described, the well is something we do on Earth all the time, and there is wind power on Mars to be used in the nighttime or in the polar regions in the winter. Okay, so let's turn to water, but let's just look at water coming from ice for the moment. As Kris mentioned, it's relatively available, but you have to go somewhere. Okay, if you keep landing near the equator, as we have always done, and we will do with perseverance, it's not accessible. If you go where Phoenix went, in the region above, say, 45 degrees north latitude or south latitude, it's just a few centimeters below the surface, as Kris described, as permafrost and as slab ice. And if you go up above 75 degrees or 80 degrees, there's polar caps, and that's all you've got is ice. Okay, it's easily extracted with thermal methods. I would argue that if you have to go somewhere to get it, then it's best done with boots on the ground, with people on the ground that can drive hundreds of kilometers and not try to do that robotically. Now, if I had my way, and I don't, and I won't, we'd land right on the North Pole where it's plentiful and do polar science. But that's very much a minority opinion. But I'd be happy to answer questions about that. I think it's a great idea. Now, what else do we use the ice for? Well, we turn it into water, of course, and water we use for drinking. We can use it for quote-unquote agriculture, even starting small. It's incredibly useful as a solvent. Kris mentioned that perchlorate is a really useful resource. You want to extract it from soil, you use water. It's amazingly soluble in water. You can run a biological reactor on water and microbes. And the reason I mention that is because that comes around to perchlorate again, about the only controlled way I know to use perchlorate as a fuel, controlled way, other than a solid rocket booster that goes boom, is to put it in a biological reactor. That's been done by John Coates at Berkeley years ago. And so I can imagine someone driving a rover that has a biological reactor in the back, and when it starts running down, you go out with a shovel, you shovel another shovel full of dirt in the back, and the microbes happily eat the perchlorate and make more electricity. So you can use water again as a solvent and as a medium. You can make cements, you can do all sorts of things. In the form of ice, now you can have structural material, whether it's lining boreholes, and I know this has been talked about a lot, or building the equivalent of igloos, but it's also terrific radiation shield. Now, again, you need to go and get it. So this is a, when humans are there kind of activity. And finally, maybe most important for resource transformation, you have CO and CO2, and you have hydrogen and oxygen in water. This is massively useful for chemistry. You can make almost anything with those constituents, including methane fuel. So now, instead of just making oxygen and bringing fuel, you can make fuel and oxygen if you have water. So the next more difficult thing is soil and rock. And we've heard about soil and rock. And I would argue that takes the biggest infrastructure. That's farther down the road. That's 2 or 3 hills down the road. Water, by the way, can be extracted from soil, which is way more difficult than a Rodwell well. But you don't have to go anywhere to do it. You can do it at your landing site. And again, all the minerals we've heard about, I won't dwell on that because I do want to say a couple of minutes to say a few words about MOXIE. And let me put it in front of me here. This is, of course, not the real deal. It's a nice plastic, colorful plastic model. If you were looking at the real MOXIE, you would be looking at a gold-plated, totally gold-plated device for thermal control. Although I remember asking the project manager why they were gold-plating the aluminum at JPL, and he said, well, if we made it out of solid gold, it would be too heavy. But anyway, you see a big gold-plated box with electronics and whatnot. And what you see here is the essence of it, particularly the two main parts I want to talk about briefly. This part here is a compressor that collects the oxygen, and this part here is an electrolysis system that that collects the CO2, that turns it into oxygen and CO. Okay, so a few words. Why do we need this to begin with? Well, I promise to come back to that. Everything that uses chemical fuels, whether it's us, or whether it's a rocket, or whether it's a fireplace, okay, needs to breathe. We don't think about this on Earth. We don't worry about it. Oxygen is free, it's everywhere. But if you're not on Earth, you not only need to worry about it, but you quickly realize that the oxygen weighs several times what the fuel weighs. So yeah, if there's a group of astronauts on Mars that all have to breathe and they use about 20, 30 grams an hour. Okay, if you want to burn fuel in a rocket to get those astronauts home, it's 100 times that much that you need to be generating. In fact, what we've estimated is to lift an ascent vehicle off the surface of Mars to carry 4 astronauts will need something like 25,000 kilograms, 25 metric tons of oxygen to burn 7 tons of fuel. And so that's the single biggest thing you'd have to take to Mars. So allowing the rocket to breathe, number one, and allowing the people to breathe, yeah, even more important, but much easier to do. That's why we do MOXIE. How it works very briefly. Part one is sucking in all that, very dilute CO2 too. There's not much air on Mars. You have to suck it in, concentrate it, and then you can feed it into an electrolysis system that is essentially a fuel cell. It's just a fuel cell running in the different direction from how we normally run it, in which case it's called an electrolysis system. So a fuel cell would take CO as a fuel and oxygen as an oxidizer, and you'd get out electricity and CO2. You put in electricity, you put in CO2, you get out CO and oxygen. And that's why we know how to do it. Again, I keep referring to Kris's talk. Doing things we do on Earth, but taking them to Mars is much easier than starting from a blank piece of paper. And it's the low-hanging fruit of the ISRU world because we know how to do it. The atmosphere is everywhere. We don't have to prepare anything. We just breathe in and breathe out. Final word I want to say is scaling. Currently, this version of MOXIE here is equivalent of a tree, of a modest-sized tree. And a modest-sized tree can kind of support one person at best. A little less where we're going because we're going to relatively high altitude on high elevation on Mars 2020, but this unit, if at a sea level location on Mars, would keep one person alive. We want to scale it up 200-fold to be able to fill up oxygen tanks. We've demonstrated the compressor technology at that scale at Air Squared that made the compressor here. That's a company in Colorado. At Oxeon Energy, a company in Salt Lake City, they have demonstrated large stacks of electrolysis cells capable of that full-scale system. So with the demonstration of Mars 2020 and with this new technology being developed, we're ready to roll to produce a full-size MOXIE whenever NASA is ready to send it to Mars to prepare for a human crew. And with that, I will turn it back over to Steve and look forward to discussions and questions.
Thank you, Michael. I had a quick question for myself. I noticed there's a few questions coming in online, which I will get to, but seeing Michael, you just were talking, I thought I would just ask a little bit. There are two pieces to scaling MOXIE up. One is, increasing the size, but the other one is the amount of time it takes to actually produce enough oxygen to actually do the kind of things that you want to do. Is this something that you would send a plant robotically to park on the surface of Mars for a long period of time and accumulate? Is that kind of the model, or is there some trades between size and amount of time?
I'm really glad you asked that, Steve. Because it's a subject, very much subject of the strategy or the tactics we'll use to get to Mars, particularly in the first missions. There have been over 1,000 plans developed for how to get people to Mars, starting with von Braun, and most of them start with the premise that you put everything in place first. Okay, you have the habitat, you have the power system, you have the ascent vehicle, and you do that before you send the crew. Now, given the limitations of the orbital mechanics, typically that means you launch all the stuff, the infrastructure, the camp, 26 months before you launch the people. Give it 6 or 7 months to get there. That leaves you about 14 or 15 months before the crew has to launch. And you want to verify that it's all there before the crew launches. So in that scenario, you've got, allowing for margin, you've got a year or so to fill up that oxygen tank on the ascent vehicle. So everything has been sized. When we think about extensibility and scaling up, it's all been sized with that idea that you got a year, you got to generate 25 tons of oxygen, okay? And if you do the math, that's going to come to something like 2 to 3 kilograms an hour of oxygen. And that's the kind of scaling. That turns out to be a unit that's going to be about a ton in weight itself, and it's going to be about a cubic meter in size.
Yeah, so obviously the other question, which cuts a bit to the other panelists too, is if you're going to do any sort of resource type extraction, processing, and so on, then obviously whether you're on Mars or on the moon, power is a very big issue. So are we talking, just Michael, just first off, are we talking you're going to need a fission power system to drive that? Or
we're talking about
what kind of powers are you talking
kilowatts,
about?
which conveniently is both what you need for ISRU before the crew gets there and is what has been estimated to be needed to maintain the crew once they're there for life support and all the other uses. So one power system to meet all needs. NASA typically these days is talking about kilopower reactors, fission reactors. There has been lots of discussion in the past about solar. Personally, I've been tilting at a windmill myself of beaming laser power down from the space platforms, which I think is a viable way to go. But so far, it's just talk.
So that kind of comes, let me throw that question more broadly to the panel. For the sorts of things that, for Leslie, for example, for the sorts of activities that we'd be looking at in terms of commercial scale type production, what kind of power systems are we looking at? Are we looking at a scaled up version of kilopower?
Very possibly. But then something to remember is that the main usage of power in terrestrial mining, and that's mostly breaking up solid rock, is in making big rocks into small rocks. Now, if you can choose your target material, your ore, such that it's already in the regolith, and that's a possibility, it's being looked at, then you've already got some comminution, that's the size reduction, already done by nature, which is what mining engineers look for. But at the same time, you have to remember that even though it is partly broken, you'll still have to do some more breaking up. So there will still be some crushing and grinding and sorting, even if you're getting what you want from the regolith. So there will be some power requirements. I hesitate to give actual numbers because it scales back to what is the production rate you need. And of course, there have been studies that have put out production rates, and it also depends on where you are getting the ore from. Is it from an outcrop of gypsum, which Kris mentioned, mining that Paul Van Susanti up at Michigan Tech is working on a system for that. it is a mineral that contains water in its structure, but not as much as if you could find ice and melt it with a Rodriguez well, as Kris was also talking about. So, what are the differences and requirements? And those differences also include power. So I don't want to put numbers to it, but there are choices to be made. Of course, we also need to remember at the very bottom of it all, power is the time rate of using or providing energy. And for demand power, when you really have to put a lot of force in fast, that takes a lot of energy very fast. And that's different from something, I'll bring up a mining method called block caving, where basically you just undermine, just openings underneath the ore body and then leave it sit for, in the original, anywhere from 1 to 2 years, and just let the ore body just collapse in on itself into those openings. That takes a lot lower power, even if the total energy might be roughly the same, than if you went in there and just mined through it all in little pieces.
Oh. Yeah,
Steve. Yeah, if I can chip in concerning power, I don't think it's as clear as nuclear versus solar. I think it's going to be both, and it's not going to be one big nuclear reactor. It's going to be probably a couple of smaller reactors, and it's because essentially having something small next to you doesn't require very thick copper cables to be run across miles. And you may think a nuclear reactor way small, but if you consider copper cable and that you have to run, actually this is going to weigh more than a reactor. Also, from a sort of a paperwork standpoint, it's going to take a bit of time before we get all the mission assurance or safety assurance in place to launch, assuming we already have this reactor on the launch pad. So starting with the solar arrays, I think solar is this low-hanging fruit. Sun is always there. It's not gonna go away. We can do fuel cells at night as well. So this is additional one. But I'm a believer of backup of a backup of a backup, and having fuel cells and nuclear and the solar is a way to go. And depending what you're going to be doing, you'll use either of the three sources of power.
A question for Dana and Kris probably too is, at the moment we are looking at these small commercial missions to deliver payloads to the moon, the CLIPS missions, and we know that there's a lot of science instruments on there, but there's also a lot of capability in terms of taking testbed type instruments as well for looking at various aspects of resources. I know that that LSII has kind of been looking at emplacement of capabilities there. And also with the early robotic missions, I think, Kris, you may have some role with some of those too. So do you want to say a little bit about those? And when you finish talking about those, could you say whether or not we should actually think seriously about doing the same thing to Mars, kind of MOXIE, but the next steps after MOXIE, right? At other types of resources?
Yeah, it's a good question. So let me kind of recap. There is something called commercial lunar payload services. There are 14 private companies that sign up to get contracts from NASA to deliver commercial, academic, and NASA payloads to the surface of the moon. We are flying on a mission called 19D. We don't know who the lander is going to be. In fact, we just submitted a couple of pages describing our payloads, and this is Planet VAC for sample delivery and LISTER heat flow probe. And all these other payloads, together with ours, will go into the so-called task order, and the 14 CLIPS teams will be able to bid for it and tell NASA, look, we want $80 or $100 million to fly those payloads to the surface of the moon. This is in line with, for example, how Viper rover is going to get to the moon too. We have a drill on a Viper rover, and Astrobotic just won a contract, $200 million, to place a rover on the surface of the moon. So this kind of thing makes sense. As we know, the commercial folks tend to cut through a bit of a red tape and move slightly faster. But at the same time, this is not just them on alone. There is a lot of partnership with NASA. NASA has done tremendous amount of work developing mission profiles, developing hardware. So it's private working together with public, with NASA. That's, in my opinion, a winning combination. So the question is, can we do the same thing on Mars? I think yes, but it's going to be limited to certain technology demonstrations. There are some things that you need big rockets and you need big sort of landers or something big to put on the surface of Mars. If you look at a Curiosity rover, well, it just gets bigger and bigger. Beyond Curiosity rover, there aren't many choices. The only one we have right now is Starship, right? But to put big things, you need to launch big things. But from a technology demonstration standpoint, you can send small things. You could, the MOXIE doesn't need Perseverance rover, right? MOXIE needs a lander. It could be, sort of like a MER type airbag system, right? So you put MOXIE right in the center, you drop it to different locations, and off it goes. It produces, oxygen and demonstrates that actually we can do this at different locations. And we learn about the life of the system and the different parameters. So I'm a strong believer that there is a place for these CLIPS type missions for technology demonstration, maybe for other applications as well.
Dana?
Yeah, so I think Kris said it very well, that the CLIPS program is a really enabling way to get access to space for demonstrating technology. And for systems that we're going to want to have on the surface of Mars, these have to be built up in a stepwise manner so that you demonstrate components of them and then scale those up, demonstrate ways to integrate those into larger systems and scale those into pilot plants and then to systems that would actually be used larger scale. And so by having easier access to the surface, you can do those stepwise developments and prove out those technologies as you are, developing the larger systems. Now, going to Mars takes a lot longer than going to the moon. So this is another place where I think the moon can be used as a test bed for proving out certain kinds of technologies. Not everything would translate directly from moon to Mars. There are lots of environmental factors that are different. But for those that you can demonstrate on the surface of the moon, you can do that and turn it around much more quickly than having to send something all the way to Mars. So that's a good way to get things proven out before you need them on the surface of Mars.
Thanks, Dana. There's a question from Alice Hoffman directed at Michael asking, could you talk more about the possibility of wind power on Mars, please? Is it as variable as on Earth? And what is the loss due to the reduced density of the atmosphere?
Okay, two very good questions. I would say it's more predictable than on Earth. The winds are more regular, but there are significant changes, say when you get a dust storm. But what is the loss is a really interesting question. Wind speed, the power is rho v cubed. It's a combination of the lower density, which is maybe 100 times lower than Earth, and the velocity of the air cubed, which is actually 3 or 4 times higher than it is on Earth typically. So when you put it all together, you get about a factor of 2 reduction in power compared to Earth. And, you know, Mars gets about a half as much solar power as Earth does because of its greater distance from the sun. And it turns out that's not a coincidence. That all trickles down into how much wind power is available. But building a wind turbine at that very, very low density is a bit of an art. It's comparable to what you do on Earth for capturing really, really light winds. We did put together a proposition for a small system for the North Pole winter that would be, to give you an idea, we were calling it 555. It would weigh 5 kilograms, it would work with 5 meter per second winds, and it would produce 5 watts. Scaling it up to something big, you know, then it gets mechanically unwieldy compared to a solar array farm, I think. But it could be done if you could build a turbine, you know, a full-scale turbine like you do on Earth. That's just a hard manufacturing job.
Also for Michael, Dallas Beenhoff was obviously listening to your talk and noted water alone is a source of propellant. No need to make methane. I'm not sure where he's referencing on Mars or just generally.
Well, that's certainly true. You can certainly create hydrogen and oxygen and then burn it. The stoichiometry isn't really optimal for what you'd like to do. And one of the problems is hydrogen is very, very difficult to store. So people would rather store methane, and so really some combination of water electrolysis and CO2 electrolysis is optimal. And you can even do that in one system, do a co-electrolysis and make what's called syngas out of it, for example. So many, many possibilities, but both are important.
Yeah, well, there's kind of another question which kind of related, which from Connor Gieman. What are the biggest challenges to turning water after it's been collected into fuel?
Well, I think that's actually a more established and mature technology than turning CO2 into oxidizer. Usually, I think what is most mature and has been used for space applications, and ISS are developed for space applications, has been the Sabatier process. And to be honest, I'm not the expert on it, but that takes CO2 and hydrogen, which you get from water, and turns it into methane and back to water again, so you can close the loop.
Okay, so Gary Fisher asked an interesting question. Would a tunnel boring machine be a feasible way to mine while also building subsurface habitat? Who wants to take that one on?
I'd like to take that one.
Okay, Leslie?
I used to do research, well, I still do, on tunnel boring machines and things like that. The general idea of digging in bedrock, so to speak, is a pretty good one. It's not something that's done lightly, and by that I mean tunnel boring machines are extremely massive pieces of equipment. It's not just the cutter head with all the tuning tools on it that rotates, but it's also all of the trailing gear, all of the infrastructure, the subsystems that are needed to take the broken rock from the working face and do something with it and get it out. Generally, a tunnel boring machine will have approximately 100 to sometimes 300 or 400 feet of trailing gear behind it. So the other thing you need to worry about is to get enough force at the cutter head to actually break the rock in a way that you can manage. You have to generally grip the sides of the tunnel. Now, if your rock, like gypsum, is not strong enough for that, then your tunnel boring machine gets stuck and you don't go anywhere. So I think in a more mature situation, not in the early stages, where you can probably work something out, but it's not something we'd want to send up anytime in the first, as Michael said, not first 1 or 10 missions, maybe the 20th mission or something. And even that would be a really small one, what they call micro tunneling.
Mm-hmm. Thank you. No other comments about boring holes on Mars? Kris, your microphone's off.
Comment. TBM, in general, they work. It's not a bad idea, but you have to, as Leslie said, it's a big thing. You can make smaller TBMs too, but you have to get them on the ground in the first place. So you need to make a hole big enough to. So I don't think it's me the noise. You have to make a hole big enough to actually go below the ground, and then somehow assemble this entire system. So it's not a trivial. But I want to mention something, that there is there is a different method from what Redwater is doing in terms of melting, which is sort of a combination between Redwater and the TBM, and that's something actually that we have been investigating here as well. And it is a method where you get down to the ice, and instead of melting and pumping water, you actually horizontally cut much larger cavern with the cutters. So you're creating snow, and then you're using a compressed CO2 from MOXIE's compressor to blow the snow to the surface. Snow, sticks around on the surface for a long time on Mars. So you can have a pile of this stuff, and whenever you want it, you bring a truck, load it up, and send it to your ISRU system. But nice thing about this sort of approach is that you do not need to dump a lot of heat in the first place to melt it. You only dump heat when you're actually ready to go through your ISRU system. Our Redwater is around 35% efficient, so we're wasting 60% goes through thermal dissipation from the ice block, and the rest of other thermal leaks. But if you don't have to melt, you don't have to worry about the chloride corrosion, or having your system sealed. It's I think sort of, again, a combination between TBM and the dry Redwater, which we call the red ice, it has a merit.
Yeah, and of course, if you have humans there and you land them on the North Pole, as I suggest, I'm sure Leslie would agree that the most energy efficient way to cut up ice is in large chunks, not in flakes. And you cut it with a chainsaw, and that's how you make ice blocks.
Yeah.
So something else to think about.
Steve, you mute.
So it's my turn. There we go. So just one quick question at the end. We're almost done on time here. But when do you think, just very quick, when do you think we'll see our first commercial production of resources we can use on the Moon or Mars? What year do you think that will happen?
My answer is we'll see it when we see it. I don't like giving years because you never are right.
We could do it in 15 years.
Yeah.
Will we? That's, again, as Leslie said, that's a political question I can't answer.
Okay. Dana?
I think it will happen soonest if we have a cooperative effort between industry and government, where we know that NASA wants to go there and use these resources, and so the industry has the motivation to develop those technologies. And then once they have it, then it's available for everybody to use, and that will really get things going.
Kris?
We'll see it next year with MOXIE. So that's the right answer, right?
Commercial. I think the question was commercial.
For commercial. Well, Mike, if you can sell this, it's commercial right there. But I think we're gonna see it sooner than later. I see momentum building up. Okay, big momentum building up. There are these commercial institutions like SpaceX and Blue Origin that are really serious about space exploration. So we're doing it completely different. Okay, what we're doing right now is completely different than what we have done in the past. So we're gonna be seeing it pretty soon.
Okay.
The most tangible commercial driver I've seen is a price point being set for a fuel depot in orbit. We'll pay so many, $500 a gram or whatever, for water, or kilogram for water. And I know I've heard that from ULA and other people. And that's a direct commercial incentive if you can figure out a way to get water from asteroids or from the surface of the moon or something to a fuel depot. That will sell.
Mm-hmm.
Say,
Well, thank you
Michael,
all.
if you sell any of that water, are you going to deliver it?
Oh,
That's the trick. That's right. Like Amazon knows that. Delivery is where it's at.
mm-hmm. Well, thank you all very much. This has been a very interesting and informative discussion, and I want to thank all the panelists for their presentations and their thoughtful discussion.
And Steve, thank you, and it's been fun.
Thank you. Enjoyed it.
Yes.